So now let's look at the full wave rectifiers, or they are also called full bridge rectifiers. Okay, so here you see a commercial three-phase full bridge rectifier, and you can search for that code for the voltage and power ratings. But anyway, so inside that package, that is a single package, inside that package there are 1, 2, 3, 4, 5, 6 diodes. Okay, 6 diodes, and you have like 1, 3, so these are line 1, line 2 and line 3 connections, and this one is the DC output. So you just get one package, and that package contains like 6 diodes. Of course, it is possible to build a full bridge rectifier using 6 discrete diodes. So let's look at the circuit diagram, right? So the circuit diagram is like that. So we will have 6 diodes, and again this is our grid side, and for that you have the inductances, and this is your output filter, this is your resistances, load resistance, so on. But anyway, so it is really similar to single phase rectifier, right? These are called legs, right? So you have in the single phase rectifier you have 2 legs, and you are connecting your L1 here, and also your second phase to here, and this is L2, right? And then you connect your output load or whatever to here. So the only difference here is the addition of the third leg. So if you have a single phase rectifier, and you can just add an extra leg, right, and you can connect that part to L3, and now you get a full bridge rectifier. So that part is the first leg, second leg, third leg, and the midpoints, this is L1, this is L2, this is L3, and then you have a 3-phase full bridge rectifier. And again, that circuit is quite common in practical applications, in industrial applications. So let's try to analyze that one, similar to what we did with the half bridge rectifier. So for now, let's ignore LS and with the ideal grid, and let's redraw the circuit. So it is nothing different from the first one. So I'm just drawing that one. If you look at that one, so this is like a half wave rectifier, and there's another half wave rectifier but connected in opposite direction. So I'm just redrawing. Those two circuits are ideal, so I just put it like that and like that. So here you can see it more clearly. So this part is like a half wave rectifier, and this part is also half wave rectifier. Okay, so you have now a symmetrical condition, and of course the voltage at that one, let's say positive voltage, and all the diodes directions are in negative direction, so this will be some negative voltage here. And I can put a virtual, I will talk about that in the following slides. I can put a virtual neutral here, and I can say the voltage here, VPN, okay, is equal to VNN, capital N and small n, but they are in opposite directions. So if I want to calculate the output voltage, from symmetry, you can just see the output voltage will be twice of the half wave rectifier. Don't worry if you are confused, I will show you the figures, right? So let's ignore the second part now, and let's look at the first part. So let's draw, this is the same figure like with the previous one. So this is the half wave rectifier, okay, and this is VAN to A2 neutral. I mean, this is a virtual ground, but we will prove it shortly. So you will have AN voltage. So whenever the, V1 is largest, D1 are in conduction, so our output voltage becomes V1. So it is identical to what we did in the previous slides. And now you have the second, you have the third. Okay, and for the bottom part, okay, let me use the blue pen. And for the bottom part, it is the same thing but in opposite direction, right? It is the same thing. Let me clean that part. If I am defining my voltage, from here to here, right? So whenever you have largest but in the negative direction, so in the smallest in that manner, so the D2, let's say, it will be in conduction, and in other words it will be D6, and in other way it will be D4, right? So from that point to that point, the voltage waveforms will be like that, right? But of course, this is just with respect to our virtual neutral point. If I want to calculate it, the actual output voltage, actually my VD is here. So VD is equal to VPN minus VNN. So geometrically it is like you need to subtract that one and add to that one, or in other words, the VD voltage is that voltage, right? So this is VD, and this is VD, blah blah blah. And if you look closely, I will show you the other slides, but what is actually our voltage? Okay, so if this is VAN, okay, we will get rid of the neutral line now. If this is VAN, what is this voltage during that time, right? So it is VAN here, and this is, remember, VBN. So that voltage will be VAN minus VBN. And actually, if you subtract that one, you can see that voltage is equal to VAB line to line voltage, right? I will have, during that instant, that value will be VAB. And after that, now I am in that region, right? So in that region, I still have VAN minus, okay, now this is VCN minus VCN, and that is VAC, right? This is A to C line to line voltage. So it goes like that. And how many combinations that I have? I have VAB, VAC, but then after here, then I have, for example, that part is now VBN minus VAN, so this is VBA, okay? So it is VAB, VAC, all possibilities not in sequence. I have VBA, VBC, I have VCA, VCB. I have 6 possibilities. I will show you an alternative. If you are confused, I will show you the put myself here, okay, these. So if you plot that lines, okay, you will have that kind of an output voltage waveform. And here, okay, every part is like, this is minus 30 to 30 degrees, so this is 60 degrees. So each section now composes of in 60 degrees waves, and you can see all those things, okay, that part VD is, what was it, VAN minus VBN, so this is VAB, and that part VAN minus VCN, so that part is VAC. And if you look at that part, VBN minus VCN, so this is VBC, and that part, okay, is VBN minus VAN, so this is VBA, and so on. So it is like all different 6 possibilities. They are all conducting in 60 degrees parts, and you will have VD output voltage. And of course, you know, from the mathematical point of view, either we will do that one as well in the following slides. Either you can calculate that area and calculate the average voltage, or what you can do geometrically, remember that was the green area that we just calculated for the half wave rectifier. So you have that area, you know, you have that area as well, you have that area as well. In the half wave rectifier you have 1, 2, 3 of those things, but now I have 4, 5, you know, 6 of those things. So you can quickly estimate, so the average voltage of the full wave bridge rectifier will be twice of the value what we had in the half wave rectifier. Okay, so it will be twice of the half wave rectifier, and remember the half wave rectifier was 3 square root 6 divided by 2p V phase, and this will be twice of that value, so you have that voltage, right? And that can be, you know, that can be, this is phase to neutral voltage, and you can write that one in terms of the line to line voltage. V phase neutral is equal to V line to line divided by square root 3, and if you do that, it is 3 times square root 2 divided by VLL. Okay, and that one, you know, that part is equal to 1.35 VLL. And if your line to line voltage is 400 volts, or you can calculate it from 230 volts RMS, okay, so that will give you a 540 volts for a 400 volts grid. So using a 3-phase diode rectifier connected to a 400 volts grid, you will get a 540 volts DC voltage, and this is twice the value of the half wave rectifier. So let's calculate the output voltage from a different point. Maybe it is easier for some of you to use that representation. So let me clean up those parts. And if you look at the output voltage, right, so there is 2 ways for first phase current to flow, either from D1, okay, or it can come from D2, D4. Okay, if there's some positive current coming from D1, if there's some positive current coming from the first phase, it will flow through D1, and if some negative current is coming, then it will come from D4. And the same thing is for the second phase and the third phase. And whenever, for example, that one is in conduction, and then let's say D2 is the return path, right? So we are having V1 and so D1, and D2 is the return path. And again, you know, just get rid of all those things and assume you have some DC current for now. And if this is in conduction, then you have the VA voltage, because that part is connected to here, and if that part is conducting, so this point is VC, right? And the voltage difference between these two will be equal to VAC, okay, line to line voltage, line voltage for some time. And after some time, I don't know, and you know, phase voltages are changing, and now let's say first phase is still in conduction, but now the return path is changed not from VC, but now is coming back from here. So now in that possibility we have D1 and D6 are in conducting, so you have VA here and VB here, so the output voltage will be VAB, line to line voltage. So you have two possibilities for here, two possibilities in results. There are 6 different voltages, right? So whenever that line to line voltage, so you have VAB, VAC, you have VBC, VBA, VCA, VCB. So you have 6 of these different line to line voltages, and of course that one VAB and VBA just inverse of each other, so it's the rectifying bit. So whenever those things have the largest value, so they will get into the conduction, so we will see it at the output voltage, right? So the output voltage, if you are looking from not to phase to phase voltages like that, but if you are trying to look from the line to line representative, so you have those things. These are not phase voltages, these are line to line voltages, right? And you can see, let's say this is VAB, right? So if this is VAB, and let me draw the axis, so this is your axis line, and you can see that one is just inverse of that one, so this is VBA, right? And let's say the next one, I don't know if is it correct or not, let's say this is VB something, okay, VBC, I don't know if it will be the correct one, but anyway. And then you will have the negative of that one, VCB, right? And then you will have VCA and VAC here, right? You see, maybe I made a mistake, but that's not really important. The important part is you have all 6 variables. So let me plot here. So you have first and second, so this is your 2p here, and in like one full cycle you have 1, 2, 3, 4, 5, 6 of different voltage waveforms. And remember, in the half wave rectifier you have the you have the 3 phase voltages, and whenever they have the highest value they are getting into conduction. So we have the same thing, whenever those 6 configurations have the largest value, so in this case that part, and in this case that part, right? In this case that part, so it is the output voltage will be jumping from peak to peak from all those different combinations, okay? So this waveform will be my V out. So that is important, and output voltage will be following my line to line voltages, and that value is square root 2, okay, that is square root 2 400 volts, okay? So let me write that, not 400 but V line to line RMS, okay? Of course, in order to calculate the average value I have to find the area under that one. So from the previous case, I have that area now, that green area. I have that green area, and I have not 3 of those, but I have 6 of those things. So if I can calculate one of those areas, I can multiply it by 6 times and I can divide it over 2p. So my question is, okay, again, as a simple question, if this is let's say 0, right, for that one, let's focus on that figure, or let me delete all those parts, it will be easier. Okay, and this is 2p, and we are looking for that line for now. So this part is p, and what is the angle of that part? Okay, it is A, I don't know, 30 degrees, B 45 degrees, C 60 degrees. Okay, so again, you know, that part is 90 degrees, so that part is actually 60 degrees. Okay, 60 degrees. So in other words, that part is pi over 3, right? So, and from symmetry you can say that part is 120 degrees, or it is 4 pi over 3 degrees, right? So let me clean that part a little bit. So what I am trying to calculate is, again, for that line it is going up, and that part is 2p. So I'm trying to calculate that area, right? I'm trying to calculate that area. This is just the, you know, symmetrical bit, and I will calculate that area, and I can multiply it by 6, and I can get the average voltage. So again, let me get rid of myself. So for that, you know, you can either write if this is again that waveform is equal to square root 2 VLL RMS times sine omega t. So, and this is, remember, 60 degrees, and this is 120 degrees, and each of those things are, you know, just a double check, that is 60 degrees, so I have 6 of those things in full cycle. So I can write V average is equal to from 60, so pi over 3, to 120 degrees, so it is 2 pi over 3 square root 2 VLL RMS times sine omega t d omega t, and I will have, you know, 1, 2, 3, 4, 5, 6 of those things divided by 2p. Or you can basically write the same thing as, you know, one of those things over 2p over 6, or pi over 3 degrees. That's the same thing. Okay, you can calculate that area, but again, let me ask you a simple question. And if I can move that waveform, okay, so it's just a geometry trick, so I can move that thing, and let's define the 0 degrees here. So I'm just transferring that waveform to here. Okay, so now it is not a sine, but it is a cosine. You know, it will be, you can do that one, there's nothing wrong with that calculations, but that one is easier, let me say. So now this is a cosine waveform, and let's say that one is 1. Okay, again the magnitude is 1, Okay, so what is that green area? Okay, so that one, remember that all area was 2, that all red area, that was 2. What is that green area? So I don't know, let me write A is square root 3, B is square root 3 over 2, C is 1, D is 1 over 2, right? So again, that is quite a useful thing to remember, and I will just give you a couple of seconds to calculate it yourselves. All right. So let's calculate it together. So now let's write that one as the cosine. This is what's that area? Area is equal to now this becomes minus 30 to 30 degrees, right? So now it is minus 30 to 30 degrees. So I can write that area as minus pi over 6 to pi over 6 square root 2, or let me calculate that one, not square root 2 for the area of 1. So this is cosine omega t, right? And that one is equal to what is the integral of cosine? So it is sine. Okay, so that one is equal to sine omega t, and pi over 6 to minus pi over 6. So you can write sine 30 is 1 over 2 minus minus 1 over 2, and that one is equal to 1, right? So that is another important thing to remember. So if a sinusoidal area, okay, if that area is equal to 2, the magnitude is 1, right? And if you have a sine like that from 60 to 120 degrees, right? So that area is 1, right? So that is just half of that area. So if you have a, I don't know, sinusoidal shaped cake, so you can either divide the cake by half from here, or you can have 2 pieces, and that green area and the other 2 pieces will have the same area. Okay, that is, one thing to remember. Of course, you can calculate it easily using the mathematical relations, but it is sometimes easier to think geometrically. Anyway, let's go back to our calculations. And now let me get rid of those parts. Okay, so now the magnitude is not 1, but the magnitude is similar to that one, square root 2 VLL, right? So that area, green area, or I can calculate V average is equal 1 over 2p over 6. Okay, if that area is 1 for 1, so now its magnitude will be square root 2 VLL, right? And I can calculate it, and that one and that one cancels, so it is 3 over p square root 2 VLL. Okay, this is exactly the same result that we obtained from the other analysis, and this 3 square root 2 VLL divided by P is equal 1 over 35 VLL, and if this is 400 volts line to line, then that gives you 540 V DC voltage, right? So that is twice of the half bridge rectifier, and actually the waveform is following the line to line voltages. I'm sure you will get more familiar with that with the simulations and other calculations. Okay, so yes, that's all for today, and we will continue with the current characteristics in the next lecture.